So I would like to welcome all of you to this workshop. I just want to make short note regarding the competition, which will be at the final day of this event. So this competition can be performed by a single person or small teams up to 3 persons. So during this workshop, you can communicate with each other and find your future teammates for this competition, for example. Okay, so this topic will be about the virtual screening in drug development. It is just a general overview on the field, on the applicability of different methods and examples of their usage. So Carl already shown you the general workflow of drug development. So it started from the identification of a target, then finding some hit compounds, which are developed to leads, which are optimized to clinical trials and develop a real drug compound. And actually, in silico tools are very useful on early stages of research to identify hits, leads, and optimization of leads. And virtual screen is particularly very useful in identification of hit compounds. And why? So why is drug development is a challenging problem? So from one side, we have a chemical space. So we have a certain number of all possible chemical compounds. And the size of this space is really, really large. So we estimated it's up to 10 to power of 40 compounds, which correspond to Lipinski rules. It's quite a lot. And at the same time, the biological space is represented, for example, by human proteins, which are already available and identified, which are something like tens of thousands. And on intersection of these two spaces, actually drug development exists. So we need to find some compounds, select from this vast chemical space, which will be active against some particular one, single, or multiple proteins in human body. And just to understand better the difficulty of this situation, because these numbers are just numbers. Just for comparison, if you measure the age of the universe, it is much, much less in seconds than these compounds. So if you will start to test and even enumerate these compounds, it will take a lot of time. And that's why we need somehow to rationally select compounds for future development and testing. So here are just examples of the available databases of compounds, which are, some of them are commercial, like CAS or Reaxys databases. Some of them are free, like a PubChem, and they contain already quite a lot of number of compounds available for researchers. Not all of them, of course, organic, so there are quite a lot of inorganic, catalysts, and so on, but there are quite a lot of them. And this is a number of virtually enumerated compound libraries. So a group of, I forgot the name of this person. That's bad. So they just enumerate all possible compounds with up to 17 heavy atoms in their structures, and those heavy atoms are just carbon, oxygen, nitrogen, phosphor, halogen, sulfur, and so on. So just so-called organic elements. Yes, actually. Thanks, Carl. This is quite famous group. And they started to develop, for example, from GDB 11, 13, and now 17. So this is the most comprehensive virtually enumerated library up to date. And it contains 100 billions of compounds. And even this is not a systematic enumeration of this chemical space. So after they reach 11 atoms, they reduce it with certain rules to reduce the number of generated compounds, because the number of compounds which can be generated really enormous. And even this is just a small and very, very small part of the whole chemical universe. So that's the game. And what we can do in this case, so we can apply some experimental screening with high throughput facilities. It is quite nice. In our institute, you will see this robotic system. It can pass up to 1 million of compounds in a reasonable amount of time. But it is quite costly. Yeah, Carl showed you that it is cheap for quite simple testing like cytotoxicity. It's really quite cheap. But for more complex assays, it is much more expensive, and it will not be possible to test even maybe 10,000 compounds. For academia, for industry, it is affordable. And also, not all targets can be formed in an appropriate format for HTS as well. So HTS is usually performed as cell-based or biochemicals. So sometimes it is not possible. And virtual screening is much more affordable because the number of compounds which can be screened is larger, and the computer facilities is also larger. We have now powerful cluster in Ostrava, which are supercomputer of the Czech Republic. In our institution, we also have our small cluster, and this makes possible to screen billions of compounds, and this is affordable for us. And now we start discussing from this virtual screening. So in what cases, what tools we can apply? So if we consider 3D structure of a target available in a PDB database or for your own experiment. So if you don't have this 3D structure of a target, then you are limited just to ligand-based tools. Okay. After that, if you have just one active compound, you already can start your in silico screening. You can perform similarity search, found compounds which are similar to this one molecule, and perform further. If you have just few actives, you can develop pharmacophore models. If you have actives and inactives compounds, you can build machine learning methods, so-called QSR models. And if you have a 3D structure, you can perform the structure-based methods, like a docking and pharmacophore search as well. So we will discuss in more detail, step by step, all these tools. So first, we will focus on the similarity search. So this method can be applied if you have just one active compound. That's enough. So the general principle are quite well known. So this is a similarity principle that similar structure should produce a similar biological effect. So these compounds are quite similar and they have quite similar biological effects. So that's understandable. And how this similarity search is performed? So you have some reference compound, which are, you know, it is active. You have some library of virtually enumerated or really existed compounds. You calculate some similarity measure between this compound and all these in this database, rank them, and select top compounds for your experimental validation. This is a very simple strategy, and this can be performed very fast. But the question is how to compare the similarity between two compounds, because it is quite obvious. So if you look on these compounds, you can say that they are similar, and these compounds are also similar. And these compounds, this and this, probably similar, and these are dissimilar. But these conclusions made just on the structure of these compounds. But if we look at the biological effects of these structures, we will see dramatic difference. So yeah, these two structures are similar in the structural, from the structural point of view, and they have the similar biological effect. These two structures have the completely different effect. So thalidomide is a quite known story that this drug was developed, and after launched on the market, a serious teratogenic effect was discovered for this compound, and this teratogenic effect was caused by the possible by enantiomer. of this compound, and it was launched as a racemate, so it is a mixture of compounds. And actually, this compound racemizes very quickly. Even if you separate one enantiomer, it will be quite quickly in a human body racemized, and you will have racemic mixture. So one compound is like a drug, another like a poison. And here is also tirofiban is a marketed drug for inhibiting platelet aggregation. And if we just make small modification, just obtain this methyl ester, such attempts were made in order to develop orally bioavailable compound, because these are compounds used as injection. And when they protect with ethyl group, the carboxylic function, they observed some serious side effects like thrombocytopenia and some others. So small changes, but dramatic effect. And actually this eptifibatide, which is a cyclic peptide, it's also a marketed drug, and it uses for the same exactly target as a tirofiban. So they are in antagonists of fibrinogen receptor, but there is almost nothing similar between these two compounds. So probably it will be possible to find easily, like by simple similarity search, these two molecules. So I just wanted to point you out that this problem is really complex. So when we thought about the similarity, we should somehow rationalize how we measure it. And these measurements depends on the representation of our compounds. Particularly, we can, if we talk about the structures, we can represent with different fingerprints, structural keys, and so on. So we just generate some numbers which represent our structures, and then we can calculate different similarity measures, which are just return you a number from, for example, 0 to 1, showing how your compounds are similar. Here I just provide several examples of Tanimoto measure and dice measure on different fingerprints for these two molecules, which looks really similar. So the difference is just one methyl group. It's almost nothing. But for some fingerprints, the similarity is not so high, for example, like for another. And the numbers also may be different for different measures, which were used to calculate the similarity. So I just wanted to show you that when you perform the similarity search, you should understand what representations to use and what measure to use, because in this case you will return different values, numbers, and even rank of compounds can change. During the tutorial, there will be short example how it looks like. Here, just one example from the literature of one of application of the similarity search. So researchers, they have lead compound, which are agonists of CCR5. They screen 60,000 compounds using the Morgan fingerprint, select 100 compounds from the top similar, from the most similar ones. They purchase them, test, and they discovered two quite nice compounds which were more active than the initial one. It can be said that it is quite primitive strategy, but it works. Even this strategy works. And there are not so many similarity between these if you look by eyes. So there are some general substructures can be found, but in general, it is quite nice. So it derives you really new structures. It can derive you, produce you new structures. So what are the advantages of a similarity search? So it needs really a little number of information. Just one active molecule is enough to start this kind of calculation. Then it can retrieve you different chemotypes, and it can be used for scaffold hopping as well. So you can really find some new chemical entities which will be patentable. But at the same time, similarity search is more conserved, I would say, and sometimes it will return you compounds too similar to your reference one, and this can be lower your patentability of this compound. Similarity search is very fast. There is a library, ChemFP, developed by Andrew Dalk. And I communicate with him, and he told that his software can screen 1 billion of compounds, and it is affordable. And it is quite fast on a desktop machine, so you don't need even cluster for that. So yeah, and again, so it is important which descriptors and similarity measure was chosen, and that chemical similarity isn't always corresponds to the biological one. So, of course, if you take the top similar compounds, you cannot expect that all of them will be active, of course, but some of them should be. So you just, in virtual screening, you just enrich your selected list of compounds with true actives. This is the main goal of all virtual screening. So it is quite difficult to expect that during virtual screening you really discover a drug or 100% active compounds. That's almost not possible. But some suggestions for further development, it would be possible to find. So the next tool is a pharmacophore search. It can be applied if you have 2, 3, or more active compounds. That's enough. And what is the pharmacophore? Probably this concept is well known. So it's just the combination of features, electronic and steric features, which are responsible for the protein response of a compound. Here are just some examples from the very early representations, how researchers thought about pharmacophores and what are these. So the first example is an explanation why sulfonamide works as a bacteriostatic agent. So there are some similarity in the distance between these groups and this one, negatively charged, because this compound is similar to the paraminobenzoic acid, which is included in the cells in the living cycle of a bacteria. And when this sulfonamide replaces the benzoic acid in a life cycle, bacteria cannot, how to say, they didn't kill them. It is a bacteriostatic, so they cannot divide and grow. Another example, for example, how researchers can explain why 2 enantiomers of epinephrine, one of them is adrenaline, works and not works. For example, adrenaline has much more potent and has much more stronger effect on a human than its enantiomer. And researchers explain it that this 3D structure reorganized in such a way that there are possible PP contact and ionic contact and hydrogen bonding contact. And for enantiomers, one of such contacts cannot be possible to achieve. And that's why it can be an explanation why this compound is less potent than this one. So this is just a very, very basic representation. Here is a nice example how atom and pharmacophore alignment compare. So here are just 2 fragments of 2 compounds which are act on the same protein. And if you look, here is the donor and acceptors are labeled by these arrows. If we try to superpose them on the atom by atom basis, we will see the same picture. This is such a picture. So, and you will see there are some contradictions. So not fully correspond these patterns, but these compounds act on the same protein. So probably the patterns should be the same. And if we flip this molecule in a plane of board and then superpose those 2 structures, you will see the perfect correspondence between these 2 pharmacophore patterns. So that's another example how to measure similarity. So these are similar, but not in such a way, but in this way. Usually when we say about the pharmacophores, we think about the feature-based pharmacophores, so pharmacophoric feature, hydrogen bond donor, acceptors, hydrophobic or aromatic feature are represented by some spheres in a 3D space. They can be directed or non-directed, for example, in the case of the hydrogen bond donor and acceptors. And it can be produced for a structure of a complex, ligand protein complex, as well from just the structure of a ligand. Here is an example of a structure-based pharmacophore derivation because, as I mentioned, it can be applied. So if you have a structure of a complex, ligand and protein, you can detect automatically with modern software the important contacts between your ligand and the protein, and then formalize this contact in a pharmacophore model. It's quite easy, automatic, and very fast. And these pharmacophore models already can be used for screening. If you don't have a structure of a complex, just the structure of your ligands, the task is a little bit more difficult. So you start with a list of active compounds, active ligands. Then you should generate reasonable conformers for them, assign pharmacophore feature to each conformer, and then try to align one by one these conformers of different compounds in order to find the common features which are map all active compounds you align. Then you need somehow to score these pharmacophores and validate them on an external test set to be sure that these pharmacophores are really reasonable. And this can produce several pharmacophores for different ligands, and you can consider to somehow combine these pharmacophores to find more general patterns. For example, this pharmacophore derives for this compound, this one for another one, but these both compounds bind to the same target, and you can find the common features. So you can combine these two pharmacophores and find common features. This can be useful for generalization because sometimes pharmacophore models, especially derived from the structure-based representation, can be very specific because it can detect a lot of contacts which are maybe not so important for ligand recognition and binding. Here is an example how we applied such a model to develop compounds which will be antagonists of fibrinogen receptor. So we collected a list of compounds from the Campbell, active ligands, and then tried to use all of them to derive ligand-based model. And we result in such a simple representation. It was quite trivial. So here is the center of a positive and negative charge, and donor and acceptor feature. It's very trivial, and you can expect that there are quite a lot of compounds will fit this pharmacophore. And this just may know that probably compounds which are active against this target have different bind modes, and compounds having different bind modes, they push on different buttons inside the cavity, but they trigger the same effect. And how to derive this? We use clustering of pharmacophores. So all compounds represented with their pharmacophores were clustered, and for each separate cluster of compounds, we build the same ligand-based pharmacophore model. And in this case, we obtain more complex pharmacophores having more than two features, and they already work. So we validate them on an external test set and show that they have quite nice precision and recall values. So they really define active compounds. And this is just one of the possible explanations, and those compounds belonging to different clusters have really different binding modes. That's why sometimes it is reasonable not to analyze all compounds as a whole, but split on a subsets on a reasonable basis to discover such things. Here is an example how a pharmacophore model can be used. So these are examples to find compounds similar to urotensin 2, which are potent vasoconstrictor. Researchers performed alanine scanning, so they replaced every amino acid in this peptide with alanine, measure its activity, and found that these 3 amino acid residues are the most important for effect. After that, they perform NMR measurement of urotensin 2 in a solution and find some constraints, possible contacts and 3D structure of this protein. They performed some molecular dynamic simulations to be sure, and from this NMR data, 3D, they derived most important contacts in their opinion and derived 3-point pharmacophore model, which is quite simple as well, and performed screening of the database of a commercially available compounds. They identified 500 hits, and one of those hits were quite active, small compounds. And if you will look on this one and this one, there are almost nothing similar. So that will not be possible to detect this using the similarity search or even by human eyes. But pharmacophore model can do this quite easily. And pharmacophore screening is quite fast, so it can be affordable to screen millions of compounds, even on a powerful desktop. But nowadays, for example, ligands could provide facilities for HPC computing, and this can be done even in just minutes, such a screening. Pharmacophore models return you a qualitative output, so it cannot say that this compound will be highly active or moderately active. It's like a simple classification. So it returns you actives and inactives one, and you just consider the list of actives and hope to find some useful hits. Pharmacophores can be used for scaffold hopping. It is quite efficient because it is very abstract representation. It's just the features, and it doesn't know about the chemistry, which can be represented by these features. And then computer or human are free to design compound which fits these features with different scaffolds. Scaffold is just the core structure of your molecule. And as I mentioned, structure-based pharmacophore models can be very specific. That's why when you develop pharmacophores from the ligand protein complexes, you have to decide which features are really important and which are less important. Nowadays, in the ligand school, they develop molecular dynamic simulations to perform MD, to develop MD trajectory of your ligand in a protein and detect the most important features which are responsible for binding of your compound, because the crystal structure is just a snapshot of a dynamic system of a protein and a molecule, and it can really detect just chance contacts. And yeah, there are many issues with the ligand-based modeling for pharmacophores, especially they related to conformational sampling of those compounds, because when you develop the ligand-based models, you have to be sure that your conformational sampling is reasonable, and you will be really sample some conformers which are close to those ones which can be observed inside of a protein pocket when compound is bound, and it is not a simple challenge. But it works. It works, and it works very fast and very efficient. Another story is machine learning methods, which can be applied if you have already enough number of actives and inactives. So these methods try to somehow discriminate actives from inactives. And it is also quite powerful, and it can screen millions of compounds, these models. nowadays. So just a general overview on this field. More detailed lecture will be tomorrow. So the goal is to find the correlation between some activity value and the structure. And directly it is quite difficult to find this relationship. Therefore, usually structure is represented with some numbers, encoded with some numbers, and then machine learning methods try to find a mapping of those compounds represented by feature vectors with the activity value. Here is another example of. These are just the overall QSAR workflow. I will not discuss it today, so I just point out that the model training takes very small part of the whole research, so the most time you should spend on the data preparation and curation for your models. And I just want to point out on the 5 important principles for QSAR models which can be used for regulatory purposes by OECD. So they should have a defined endpoint. They should have an unambiguous algorithm, a defined domain of applicability. So it means that models cannot predict everything in the chemical space. So they have subspaces where it is more confident than in other, and this should be defined for model. It should be also have an appropriate measures of goodness of fit, robustness, and predictivity. So this model should be validated statistically to show that they are really useful, at least for in retrospective validation. And if possible, those models should be interpretable to understand better the reasons of model make one or another decision. So here just example of very simple QSAR models. The first QSAR equation developed by Hanch is represented the correlation and relationship between the 2 simple measures, lipophilicity of your compound and Hammett constant. And it is enough to predict the inhibitor activity of phenylacetic acid on plants' growth. It's quite nice concept. So you just need 2 variables and you can predict the property of your compound. But of course, the applicability of such a simple question trained on a limited number of compounds is also limited. Another example of the quite old and famous model is the free Wilson. So if you have a common scaffold of your compounds, you can represent changed parts with some labels and encode them in such a way that these are variables which are indicators. They can be 0 or 1, meaning that presence or absence of a particular substituent at that position. And then you can just create the same linear equation with the coefficient. And if you have a same compound with the same scaffold but with a different substituents, you can substitute these descriptors with 0 and 1s corresponding to your structure and predict the property. Of course, this equation is also limited in usage because it is limited by the scaffold and the diversity of those substituents. Nowadays, of course, more complex methods are developed which can be trained on hundreds of compounds, and the number of descriptors is really large, but we talk about them tomorrow in more details. So here are just one of the examples of how QSAR models can be used for virtual screening and produce some useful output. So in the group of Tropša, they took the Cambridge database of chemicals. They calculated descriptors for those almost 500,000 compounds, filtered them according to the applicability domain of their QSAR models, which were developed before that. Just 10% of compounds pass this filter, so it shows you how models are limited in their usage. So they cannot predict reliably the whole chemical universe, just a small part. And even in this small part, there will be some errors, of course. Then they pass these compounds through the drug likeness filter, remove compounds with undesirable physicochemical properties, and the remaining part of compounds were predicted by the QSAR models, and then they selected top scored compounds as actives, and also they selected some inactives compounds for validation of their models and perform experimental screening. And they found 7 quite active hits against malaria, and one of them have a nanomolar activity. So that's quite nice. And this is also, QSAR models are quite fast, as I said, so it can screen millions of compounds as well, like a pharmacophore screening. It can produce not only qualitative output like pharmacophore, so it can be used not only to categorize compounds on actives and inactives. It can be also used to predict the exact value of activity of your compound. But of course, with some, uncertainty. So it shouldn't exactly correspond to the observed property, because even experimental values have some errors, and your developed QSAR models cannot be more correct than the used experimental data to train them. Also, QSAR models can work with compounds having different mechanism of actions. Nowadays, these complex models, like random forest, neural networks, it can be used. Because initially, QSAR models were developed only for subset of compounds which have the same biological mechanism of action. And disadvantages of a QSAR that it is, you should curate your data very carefully, because it make a major impact on the quality of your outputted models. So, because otherwise the garbage in, the garbage out. So it works in such a way. So you should define applicability of your models, and this is not an easy question. So there are a lot of measures of applicability domain exist, and there is no consensus still exist. Which one is better, which one is worse? So that's also an open question. And for QSAR modeling, it is quite hard to encode stereochemistry. So such models exist, but they're usually limited in usage. So if you have too diverse set of compounds, which include stereoisomers, it will be quite difficult to predict exact activity of these stereoisomers. Usually, everybody uses a 2D representation of compounds and forget about the stereochemistry at this point, and then later they try to develop other models, for example, using docking or pharmacophore modeling to predict the activity of those enantiomers, to model it. And the last section is structure-based. So if we have a structure of the ligand protein complexes, we can apply structure-based methods. And one of the most widely used is the docking. It is less performant than previously discussed methods, so it can screen up to million of compounds. But again, if you have a supercomputer facilities, you can screen even more if you want. So just briefly, what is a docking? Docking tries to answer two questions. What is the pose of your ligand inside the binding pocket? What is the conformation of your ligand? And the second one is energy, how tightly your compound binds to the protein. But docking is a quite difficult task due to many issues. So, as Carl told, it's like a lock-key principle, but in reality, this lock and key can be can have very complex shape, and it is quite difficult to find how to orient each other to make them in tight contacts. Also, these systems are not rigid. In living organisms and in nature, they are dynamic. They change their conformation constantly. And this also can affect your docking results. Sometimes protein and ligand can adapt conformation to each other after binding. For example, when ligand bind to the protein reduces their flexibility, for example. Also, great effect can produce solvation, because these two entities not in vacuum, ligand and a protein. They are in a solvent, in a water medium. And this is also a complex issue, because when they bind, they can distort this molecular network around the protein, make it not favorable, and this can cause a decrease of delta G of binding. So when we calculate the delta G, free Gibbs energy of binding, it's just the game playing with big numbers. So we have large number for protein, for ligand, and when we subtract these two large numbers, and because usually delta G measured in a scale of kilocalorie per mole, it's quite small. And when we subtract the energy of a complex and then energy of single protein and ligand, these are subtraction of two large numbers, and it can produce quite large errors. That's why it is quite difficult to find the exact value of binding during the docking, at least during the docking. So, as I told, we have two issues and two most important stages for docking. So we have a search algorithm which sample conformations of a protein and the ligand, and we have a scoring function which should quickly evaluate the energy of binding, because it is not possible to calculate it from the molecular quantum of chemistry, so it should be something more simple to be able to fast screen those compounds. When we talk about the flexibility can be considered on different level. The first docking programs, they consider ligand and protein rigid, both rigid. In this case, the researcher should generate several conformers of a ligand and then just try to move it inside the pocket and hopes that one of those conformers will fit the pocket. More popular approach when a ligand considered flexible, so you generate some conformer of a ligand, put inside the protein, and then the program automatically tries to find the better conformation of your compound based on the initial one. And to make this more reasonable, you should place this ligand several times with different conformations and look to which minima it will get. And even more complex representation, you can consider protein also as flexible. And this increases the complexity dramatically, and the screening process can be really slow in these cases. And usually not the whole protein is considered flexible, but only side chains, because the backbone of a protein are more or less rigid in a small time scales. But side chains can be quite flexible, for example, lysine, arginine, and so on. And modern software can do this, but of course, by the cost of your time and computer facilities if you have. To score energy and fast calculate the energy of interactions, there are several types of scoring functions were developed so far. So one of them are force fields, so they are most close to the quantum chemistry level maybe. So they use some force fields which calculates your interaction energy, non-covalent interaction. And there are several software which incorporate such scoring functions. Empirical scoring functions they can be considered like a simple QSR model. So they take several parameters of geometry of your protein and ligand interaction, and they produce some outputs. This is usually linear models or more complex, like nowadays random forest models, but it's similar to what QSR models. So they use machine learning methods. And knowledge-based scoring functions, they use just the statistics of contacts of from available PDB structures, so you can calculate the frequency of some contacts, observe it, and based on this principle you can develop the scoring function which can evaluate as this interaction is favorable or not favorable based on purely statistical enumeration of observed contacts in already known PDB structures. However, when we say about the quality prediction of energy, basically for docking it's quite difficult. As I told you, it is very difficult to reproduce the energy. And if you try to compare the scoring function with observed binding constants for different compounds and proteins, we will observe that there is probably no correlation at all. However, if you select a particular target, the situation can be much better, and you can observe some more or less nice correlation, which means that it returns you more reasonable results for this single target, but it cannot be compared to results obtained for another target, for example. But this is not the only issue. Another issue is that we showed this in one of our studies of discovery of antagonist of a fibrinogen receptor. So when we change the structure, which are constant, and we add the amino group and then extend the linker, increase the chain length, and we use plants and samples. These are two docking programs which uses different sampling method and scoring functions. And both of these docking programs told us that increasing the chain length will increase the activity and affinity of those compounds. But when those compounds were synthesized and actually tested, we observed that adding just one carbon to this chain and going from butyric acid derivatives to pentanoic acid derivatives, and we observed dramatic drop in activity and 2 orders of magnitude. However, docking cannot detect this, and when we look on these poses visually, we saw that since there are very flexible moiety, it can adopt quite nicely the amino acid contacts. So there are almost no strain energy for this chain, so it can adopt and bind. But there are 2 possible explanations why such drop in activity can happen. The first one is the flexibility of those compounds. So docking scoring functions in docking usually well estimates the enthalpy of binding, but badly estimates the entropy. And if you have very flexible compounds and you use docking algorithm, you usually observe, unfortunately, quite bad results. So I observed it many times, and even with modern softwares and scoring functions based on the neural networks, deep learning networks, all of them cannot predict this feature. So I test exactly these compounds on modern scoring function, and I see the same behavior. So elongation of a chain, improving of a predicted scoring function. But that's not the truth. Another possible explanation, which is also somehow related to the entropy factor, is that those compounds are not favorably solid. Because when we saw in a 3D visually these complexes, this chain forms like an arc, and there was some space, empty space, between your ligand and the protein, and in reality it cannot be observed, so it should be filled with water or it should tightly contact with your protein. And that's since this chain is hydrophobic, water molecule inside this space probably not very favorable, and this can be another explanation of why this is observed. This is quite annoying issue for myself actually, because we did docking quite frequently, and each time I should consider these issues of possible for too flexible compounds if we screen them. But for rigid compounds, it produces quite relevant results, in my opinion. So how we can validate docking? Because all models which we use for virtual screening should be validated, because otherwise you cannot be sure that these models are reasonable. And docking can be validated in two ways. So the first one, you can try to reproduce the crystal structure of your ligand. So if you take a complex, you put out your ligand from the cavity, from this complex, change its conformation, put it back and run docking. And if docking can reproduce the conformation of your ligand, that's good. Usually, if it is reproduce the conformation within 2 angstrom of root mean square deviation, these results considered as well. Sometimes it is not possible, and in this case you need to change the setup of a docking algorithm or consider another complex maybe, so that should be investigated. Another validation is a validation of a scoring function. It is more complex and not always possible. It is possible if you already have some subset of active and inactive molecule with the known binding constant or binding affinity to the target. You can just dock them, rank according to the scoring function, and try to find the correlation with the scoring function, or build such a ROC curve which shows you how your scoring function preferably select more active compounds than inactive ones. Because sometimes we observe that docking programs works really bad and like a random chance selection of molecules. So these are more rigorous validation, and I usually did this if it's possible, but I observe nice correlations not very often. But sometimes you can observe not linear correlation, but some monotonic changes. This is also quite good, because in this case you can rank your compounds, and you can be sure that compounds ranked higher will be more active. Here is one of examples from a literature where researchers discovered ligands of beta-2 adrenal receptors. So they took almost 1 million compounds from zinc library. This is a library of commercially available compounds. Use doc software, select 500 top scored compounds, then select just 25 of them for further validation. And for 6 of them, the binding constant was quite high, and one of compounds had a nanomolar activity. So that's really perfect result, I would say, from docking. So this is a really viable strategy, and you can use it. But from a practical point of view, I would recommend to use at least 1, 2, or 3 different softwares which implement different scoring functions, sampling algorithms, and try to find the consensus between them, or try to find the best tool, because you never know which docking tool will be the best for your particular task. Here is just the conclusion regarding the molecular docking, that it is quite fast. Nowadays, these algorithms are optimized quite well. So it can determine binding pose quite well, but it cannot calculate accurate free energy of binding. But it can be used to rank your compounds, and it is more useful. So you just need to calculate these predicted scoring functions values and rank your compounds and select the top of them. And you can expect that the top list is enriched with really active compounds, because currently the exact estimation of binding energy is quite low, in my opinion. And of course, the main restriction is that you need the structure of a protein, at least in upper state without a ligand. And at the end, I would show you one example of consensus application of different tools, because when you use just one tool, that's okay, and you can be happy with it, with this. But if you have a variety of tools, there is quite reasonable to use all of them and try to find the consensus between different tools and accumulate them to find really active compounds. However, if you use too much tools, your predictions can become quite conservative. But in this case, you will have higher chances to find true active compounds. So this is a study, another study, which is also related to the discovery of inhibitors, of antagonists of fibrinogen receptor. So we developed models, pharmacophore models, QSAR models, several docking algorithms, and also shape and field-based models. Initial screening of the available commercial library didn't return any hits, and it was quite easily understandable because, as I showed you on the previous examples, on those pharmacophores, there should be in the molecule which are active against the fibrinogen receptor, there should be positive and negative charge in their structure, which are on quite large distance. And as the commercial databases, there are almost no such compounds. So almost no compounds passed the pharmacophore filter. Therefore, we virtually enumerate the library of compounds, about 7,000, and enumerate all of them stereoisomers. So we use the building blocks with which our chemists were familiar. So we enumerate those compounds, and we pass sequentially through different filters, from pharmacophore, QSAR, docking, and so on. And finally found selected for synthesis just 2 compounds. Because we are limited in a budget, so we have to develop some active compounds by less costs. Here is the structure of those compounds. And further, we synthesize both enantiomers of these compounds and experimentally measure their affinity and anti-aggregation activity, and compare with the tirofiban, which is the marketed drug for this disease. And we observed that one compound were much more active than the marketed drug. Another one was lower in activity. But that is a successful story. So we select very small number of compounds, but with very high confidence that they will be active. Unfortunately, as I told you, since we use too many tools and try to find the consensus between all of them, those structures are not so novel, I would say. So maybe they're less patentable. We didn't perform the patent search, but if you look on the tirofiban and these structures, there are quite a lot of similarity between them. So at the end, here are just several examples of application of virtual screening for real drug discovery, and in this review you can find even more examples. So nowadays, these in silico tools are quite routinely used to assist medicinal chemists to make decisions. It can be used for different reasons. So to find some promising leads, or optimize these leads compounds. So you can read this review for more examples and inspire yourself to apply these tools in your everyday work. So this is all from my side. If you have some questions or remarks, you can ask me now or during the coffee break if you want, so it's up to you. So everything clear? Probably you are tired. Okay, so I think that we should make a short break.